Hey everybody, we're live and in stereo, so I'm gonna go over two other additional concepts that we need to quickly cover before we actually understand titration curves. And again, just like the last couple of classes, I am trying to fix the concepts that have been left, that have made you guys bamboozled in O-levels and IGCSE. Now I hope you guys know what's the difference between concentration of an acid and strength of an acid, and we know that the pH values, they actually depend on concentration rather than strength, right? And we also know that strength of the acid depends on whether it can fully ionize in an aqueous solution or whether it can only very slightly ionize in an aqueous solution, aka partially ionize in an aqueous solution, right? So I hope you guys now know that it's actually concentration of hydrogen ions which dictates the pH rather than strong acid or weak acid, because we debunked the myth that strong acid will always have a lower pH. We debunked that myth by taking a very concentrated weak acid and compared it to a very dilute strong acid, and we realized that a very concentrated weak acid actually had a lower pH, aka was more acidic, because acidity has to do with hydrogen ions K concentrations, right? Now today what we are going to do is I'm going to talk about pH in a little more detail. Again, this detail is not directly part of your course. These two details that I'm going to give you today, they are not directly part of your course, but indirectly can be tested in MCQs. I'm just teaching you guys for the MCQ purpose, as well as it's going to help you guys understand titration curves, which I know you all, some of you who've studied them, they dread it because they don't kind of understand it. But inshallah, these tiny concepts that I've given to you guys, they will actually help you understand titration curves in a very beautiful manner, right? Now let's understand pH and what a pH scale is effectively, right? So what is in fact a pH scale? Understand that the pH scale is just an artificial scale. It's a man-made scale, right? It's a man-made scale. And sir, why did we need this man-made scale? We needed this man-made scale to distinguish between an acid, to distinguish between a base, and to distinguish between something which is neutral. We wanted to distinguish between, acids. We wanted to distinguish between basic solutions, acidic solutions, alkaline solutions, and neutral solutions. We wanted to distinguish between those solutions, and we wanted to quantify it. We wanted to give it certain values, right? And that is why we came up with something known as the pH scale. Now the question is, what is actually meant by the pH scale? Before I tell you guys what's meant by the pH scale, you guys have already studied that, if I talk about pHs, acidic substances, they have pHs lower than 7, neutral substances have a pH of 7, and alkaline solutions or alkaline substances, basic solutions, they have a pH of greater than 7, and I'm going to show it to you right now, right? Before I go into any detail, please understand that these colors are inverted. These are not the actual colors. This is in fact your universal indicator, which is basically going to give you Roig Biv colors, right? Roig Biv, that's how we've remembered it back in the day. R stands for red, so strong acids are going to have a color red. Please, these are inverted colors, don't confuse them. This is not blue, this is going to be red color. Then orange, this 3 to 4 to 5 range is going to be orangish yellow. Green is pH 7, that's green of water, Blue is then pH 7, above pH 7, 8, 9, that is blue. And then indigo and violet, this 11ish is about indigo, and when you come here to 13, 14, that's about violet, right? That's, for example, a very strong base with which is very concentrated. Let's suppose NaOH, right? It's actually also an oven cleaner. They are also used to clean gutters and all, right? And pH 6, that's slightly acidic. Milk is slightly acidic. Blood is slightly on the basic end. Water, it's basically pH 7. NaCl, pH 7, that's why it's written water, salt solution. NaCl aqueous is pH 7. NaCl has a pH of 7. This is dilute hydrochloric acid. Lemon juice, a little on the weaker acidic end. Orange juice, vinegar, ethanoic acid. Ethanoic acid is basically vinegar, right? As pH 4. And lime water, that's calcium hydroxide, right? Aqueous calcium hydroxide, that's on the basic end. Bleach, washing soda, even soaps, they're all on the basic end, the alkaline end, right? And this is a pH scale that we came up with, where 0 and 1 and 2 normally represented a very concentrated or a very strong acid. Even if a strong acid is dilute, it is going to have, it says dilute hydrochloric acid. So even, and because hydrochloric acid is a strong acid, even if it's dilute, we know that it is going to have a higher concentration of hydrogen ions, and therefore it has pH pretty low, 0, 1, 2, 3. The question is, how did scientists come up with these values? What exactly does pH mean? You've all been taught in O-levels and IGCSE that you have a pH scale that goes from 0 to 14. G is green, which stands for, on a universal indicator color spectrum, G basically stands for green, and that has a pH 7, that's neutral. These three colors are acidic, on the acidic end, where red is the most acidic, and BIV, these three colors are more towards the alkaline end, where violet is the most alkaline out of all. But you've just learned this, right? That pH is a man-made scale, goes from 0 to all the way to 14. Below 7 it's acidic, above 7 it's above 7 till 14 it's basic, right? That's what you guys have all learned. But what exactly is a pH scale? Remember, in the last couple of classes I talked to you guys about pH, which basically depends on the concentration of hydrogen ions. And I was pretty smart to talk about this. I was one of the smartest people to actually talk about what dictates the pHs. And that was in fact what? That was in fact the concentration of hydrogen ions. Sir, why did you say that? You were very smart, I know, but why did you say that? I said it because pH is basically, it's how is it calculated? It's negative log of hydrogen ions concentration. That's it. And again, this calculation you're supposed to learn in A2 chemistry, but I believe that it's not so difficult, and it can easily be learned in AS level as well to understand titration curve. So I'm gonna still explain it. I couldn't care less, right? That is the reason why I said that pHs, they actually depend on the concentration of hydrogen ions, because pH is actually a measure of the concentration of hydrogen ions. It's actually a measure of the concentration of hydrogen ions. The question is, sir, why is the pH scale a logarithmic scale? Why am I putting log with it, right? Those of you who are good with math, the basic answer for that is that the possible ranges of hydrogen ion concentration is pretty large. It's very large. So it is just convenient to use the log scale to make those values smaller for us, so that we don't have to deal with values which go beyond our graphs and all of that stuff, right? So we don't want to deal with large values of hydrogen ions. We don't want to do that. We don't want to deal with these very large values for concentration of hydrogen ions. Therefore, we use the logarithmic scale to make those values smaller, so that it is convenient for us, right? That's why we use log. Those who study math, they know that log function is used to make these big ass values smaller, right? That's just a basic understanding of log. Other than that, I'm not going to go into the maths for it, but that's basically why you use log. If you just hide log from it, it's basically a measure of concentration of hydrogen ions. The only reason why I put log here is in fact to do what? To make those values small, because hydrogen ions ke concentration, they are pretty large values. So that's the idea, right? That's the idea. You could even say oxonium ions. It's also, pH is a measure of hydrogen ions ki concentration, or you could even say oxonium ions concentration. Do you know what oxonium ions are? These ions, H3O plus. Because we effectively know that hydrogen ions later on react, because a proton alone does not exist. It alone does not exist. It exists for a very split second. This H plus ion is pretty reactive. It directly is taken in by water, and H3O plus forms, which is called the hydronium ion, and you could also call it the oxonium ion, right? So pH is a measure of concentration of oxonium ions or hydrogen ions. Couldn't care less. Both are correct, right? Now this is how pH scale was developed initially, right? You just measure hydrogen ions ki concentration, right? Now, I want to derive something for you guys. Again, this derivation is not part of your course, but I want to derive it just for you guys to understand things a little better, right? Sir, pH of solution can be measured using what? Sir, a pH of solution, if you want to measure the pH of any solution, you could either use the pH probe. You could either use, there are multiple ways. You could use the pH probe, you could use the pH meter, you could also estimate it, not accurately measure it, but you could estimate it. You could estimate it using what? Universal indicator, which is, universal indicator is just a mixture of indicators. It's just a mixture of indicators, gives you a varying range of colors over a varying range of pHs, right? So you can estimate it using universal indicator. You could accurately, to much accuracy, you could use a pH probe, a pH meter to actually figure out the pH of any solution. This will quantify it for you, and this will give you colors, the Roig Biff colors, and you could estimate the quantification for it, right? You could say, hey, if it's like reddish, it'll be rough to 0 or 1, Now, how can we actually, play around with this equation? I want to play around with this equation for you guys. I'll tell you. See, I want to derive something from it. We know those who are interested in math, you will love this. Those who are not, forget about this, but this will actually help you guys. I'm not joking. It will help you guys. Okay. So negative log has a base 10 right here, right? Now, if I were to, first of all, what I'm going to do is I'm going to multiply both sides of the equation with -1. You know that if you were to multiply the right side with -1, you have to multiply the left side with -1. I just want to prove something to you. So you're going to get negative pH log base 10 hydrogen ions. And those who've studied additional mathematics in O levels, or those who've studied AS level math, you know if you were to finish log, what's going to happen? This 10 is going to come here. So it's going to be 10 raised to the power negative pH, and you are going to be left with hydrogen ions ka concentration. That's it. So this is effectively the derivation that I wanted to do for you guys, right? If you have 10, this is actually one of the formula which has been derived, which is 10 raised to the power negative pH equals hydrogen ions ka concentration, right? What this actually means is, I'll tell you what this means. What this actually means is that if you have a pH of 1, right, what would be the concentration of hydrogen ions? What is concentration of hydrogen ions? If you have a pH of 1, what's the concentration of hydrogen ions in an aqueous solution? See, just put 1 here. 10 raised to the power -1 will give you the concentration of hydrogen ions in the aqueous solution, which is equivalent to what? It's equivalent to 0.1 mole per dm cube. Right? Let's suppose you had a pH of 2. Right? A pH of 2. What would be the concentration of hydrogen ions? What would be the concentration of hydrogen ions? Sir, why do we use logs in ionization energies? Aisha, for the same reason. They are pretty large values. We want to not deal with such large values. Right? Okay. What would be pH 2? Again, 10 raised to the power -2 would be equal to the hydrogen ions concentration, which is what? 0.01 mole per dm cube. What if I have pH 3? What would be the concentration of hydrogen ions if you have pH 3? 10 raised to the power -3 would be the concentration of hydrogen ions, which is what? 0.001 mole per dm cube, all molar, right? What if you have pH 4? pH 4? What if you have pH 4? It is going to be 10 raised to the power -4. Whatever pH you have, 10 raised to the power -4, or that particular pH would give you the hydrogen ions concentration, which is what? 0.0001 molar or mole per dm cube. So it would not be incorrect for me to say that a change in, and these are all for MCQs by the way, it would not be incorrect for me to say that if there's a change in, listen to this very carefully, if there's a change in of one pH unit, if there's a change of 1 pH unit, the hydrogen ion concentration changes by 10 folds. Does it? It does change by 10-fold, right? It does change by 10-fold. The higher pH you go to, it will decrease by 10-fold, right? And the lower pH you go to, if you go from pH 4 to pH 3, it will increase by 10-fold, So this MCQ has never been tested, can be tested in the future. If there's a change in 1 pH unit, the hydrogen ion concentration would change by 10-fold. I'm using the word change, right? Here it's decreasing by 10-fold because you're increasing the pH. And if you go, in the reverse order, go from pH 2 to pH 1, you're going to actually increase the hydrogen ion concentration by 10-fold. And that is the reason, and this is so beautiful, that is the reason why if you have a more acidic solution, aka having higher concentration of hydrogen ions, you're going to have a lower pH. See, the lower concentration of hydrogen ions results in a higher pH. Isn't that beautiful, right? The less you have, the lower concentration of hydrogen ions you have, the higher the pH you're going to have, right? That's why if you look at basic solutions, if you look at basic or alkaline solutions, they must have, let's suppose let's talk about an alkali which has a pH of, let's suppose, 8. What does that indicate to you? That indicates that the hydrogen ions inside that solution are 10 raised to the power minus 8. Isn't that beautiful? Which is pretty low, right? It's like 0 followed by 7 other zeros and 1. 0.8, 2, 3, 4, 5, 6, 7 and 1. That's molar. That's the concentration of hydrogen ions. So the higher the pH you have, the lower the concentration of hydrogen ions you have, right? That's so beautiful to understand and actually absorb. Now I want you guys to do something else as well. I want you guys to do something else. And I'll even show you, before I want you to do something else, I'll show you the table for it even. Such a beautiful table. You'll enjoy it, inshallah. You all will enjoy it. Look at this table. See. Look at this. You had a pH of 0. It's okay if you don't write 1. You can write 1. It's better to write 1 here. You had a pH of 0, right? What does pH of 0 mean? pH of 0 means you have how many hydrogen ion concentration? It's 10 raised to the power 0. Negative 0 is basically 0, right? 10 raised to the power negative 0, 0. And 10 raised to the power anything is what? 1. So here, pH 0 means you have a concentration of 1 mole per dm cube of hydrogen ions. pH 1 means what? What's the concentration of hydrogen ions? 10 raised to the power minus 1 on 1 multiplied by 10 raised to the power minus 1. What does that give me? 0.1 mole per dm cube. So the higher pH you have, the lower the concentration of hydrogen ions. See, the pH is increasing, the hydrogen ions concentration is in fact decreasing, right? So would it be right to say that it increases in exponential as it increases by the exponents of 10? Absolutely, you can say that. You could say it increased by 10 folds or like this. Absolutely correct. Okay. Now, also, I want you guys to do something else for me. What is this? What is this? What is all of this? What is this given to you? It's what? It's the concentration of hydrogen ions, isn't it? It's the concentration of hydrogen ions. Isn't that true? Concentration of hydrogen ions. Now, if I say that you have 1 multiplied by 10 raised to the power minus 1 hydrogen ions, 10 raised to the power minus 1, or you could say 0.1 molar, 0.1 mole per dm cube of hydrogen ions in a solution, what would its pH be? I want you guys to do reverse working now. Before I was giving you the pH, which was, let's suppose, 1. So pH 1 means what? 10 raised to the power minus 1 concentration of hydrogen ions, right? 0.1 molar. Done. But now I'm saying you have 0.1 molar. What would be the pH? This one right here. The 0.1, first always write it in its standard state. 1 into 0.1 is 1 into 10 raised to the power minus 1. And this 1 is actually the pH. So if you have a 0.1 molar solution, right, of hydrogen ions, its pH is going to be 1. How beautiful is that? How beautiful. It also increases exponentially, decreases exponentially. It changes by 10 folds. That's the better word for it. Increase, decrease, both, Ibrahim. I just went over it. If you go in the reverse order, it's going to increase. If you go from pH 2 to 1, it's going to increase by 10 folds. If you go from pH 1 to 2, it will decrease by 10 folds. It's pretty basic, right? And if I look at all of these concentrations, if you write it in its standard form, the exponent, the superscript on 10, the superscript of 10 will be the pH. Let's suppose you have a concentration of hydrogen ion which is 1 into 10 raised to the power, let's suppose, minus 3. What would be the pH for it? What would be the pH for it? This is the concentration of hydrogen ions. What would be the pH for it? The pH for it would be 3. Right? How beautiful. What if you have 1 into 10 raised to the power minus 5 hydrogen ions? What would be the pH for it? The pH for it would be 5. Or you could say vice versa. pH is 5. What would be the concentration of hydrogen ions? So 10 raised to the power minus 5. Or you could say 1 into 10 raised to the power minus 5. Right? And that exactly is this. Right? So they are basically connected to each other. You could calculate the pH from the concentration of hydrogen ions by writing it in its standard state. Right? Or you could also calculate the concentration of hydrogen ions from its pH and the pH from the concentration of hydrogen ions. That's how basic and easy it is. Now those who get confused in these things, just use the formula for it. Although this formula is not a part of your course, it's negative log of hydrogen ions. Right? So whatever concentration of hydrogen ions you have, just put negative log in the calculator. Let's suppose, for example, can you guys do negative log of 1 into 10 raised to the power minus 3 in the calculator? You'll see you're going to get a pH of 3 right here. And there's math involved behind it, but hey, that's the idea. right? Now, if something has, now you guys tell me something. If a particular solution has pH 7, how many hydrogen ions does it have? If something has a pH of 7, how many hydrogen ions? What would be the sorry, my bad for the question. What would be the concentration of hydrogen ions? If something has a pH of 7, what would be the concentration of hydrogen ions? Right? It's going to be 1 into 10 is power minus 7. Isn't that true? And that is the reason why water has a pH of 7. Why does water have a pH of 7? Why? Because it has these many hydrogen ions. Right? And that's why pH 7 was given the neutral reference point. It was used as neutral reference point. Done? Now, my question to you guys is, will pH scale always be positive? Think about it. Can pH scale be negative, or will pH scale always be positive? That's also never been tested in the MCQs, but it can be. Cambridge normally does not play around with such basic ideas. They expect students to already know it. From up until now, you guys know that pH is from 0 to 14. This is what you've learned in O-levels and IGCSE, which is absolutely incorrect. It's absolutely incorrect. The pH can also be negative. I'll prove it to you. Let's suppose you have, and use the formula for it, please. You want to calculate the pH by saying negative log of hydrogen ions, right? And again, all these tricks that I've shown you, these are all for MDCAT and all of these things for test, anti-trust, in interviews, they're going to ask you this. Other than that, you can directly just use the formula everywhere, right? If you're given the pH, write the pH here, and put an equal to sign in the calculator, negative log, and put X there, and put in calculator, say calculate it for me. That's it. That's how I will teach you even in A2. I just ask you guys to use this equation, and that's it. But if you want to properly understand the idea, I've even given you guys the proper understanding of the pH scale idea. Now, I just want you guys to use the formula to actually debunk this myth right here. And the formula I want, and the question that I want you guys to tell me is, to answer for me is, what if hydrogen ions has a concentration of 5 mole per dm cube? 5 mole per dm cube. Can you guys calculate the pH for it? Let's suppose there's a very strong acid, let's suppose hydrochloric acid, and it has a concentration of 5 mole per dm cube. And since you know it fully ionizes in an aqueous solution, the hydrogen ions that you're going to have are also going to have a concentration of 5 mole per dm cube, right? So effectively, you have 5 mole per dm cube hydrogen ions. Can somebody calculate the pH for this? It's going to be negative log of 5. What do you guys get? And voila, it's coming out to be minus 0.699. Minus 0.699 or minus 0.7. And here you go. pH can also be negative. pH for very concentrated, strong acids can also be negative, just like for HCl. HCl already is a strong acid, so it'll fully ionize, and whatever concentration you have here is going to be the concentration of hydrogen ions, because it's fully ionized. Hundreds gives you hundreds of these, right? And for that matter, if you want to calculate the pH, you can, and it can be negative because it's so concentrated. That's why in your laboratories you use dilute HCl, because they dilute it very much. So that's another idea I wanted to debunk for you guys, which is that pH can be negative, and I wanted to teach you guys how pH is actually calculated. You'll learn more about this in A2 chemistry, more about pHs and even POHs. I love A2 chemistry when it comes to acid, bases, and so on. So there's something known as pH scale, and then there's also something known as POH scale, and this is basically negative log of OH ions concentration, and that's it. It's not that difficult to understand. It's not rocket science. This is the idea. POH tells you, measures the concentration of hydroxide ions in an aqueous solution. pH measures the concentration of hydrogen ions in an aqueous solution. The more acidic you are, the more hydrogen ions you have, and therefore the lower pH you are going to have, right? And fun fact for you guys, just a fun fact, what the concentration of hydrogen ions is in water. Water's pH is 7, right? Water pH is 7. So what would be the concentration of hydrogen ions? It's 1 into 10 raised to the power minus 7. That would be the concentration of hydrogen ions. And fun fact, do you know why the pH scale goes up to 14? for us, for our course. Why does it go up to 14? Because water actually also has 1 into 10 raised to the power minus 7 OH ions. So when you add these two together, that gives me 7 plus 7, that gives me 14. That's why you go up until 14, because 14 is actually a sum of pH plus pOH for water. So the pH of water, the pH for water is 1 into 10 to the power minus 7, right? Which is actually the concentration of hydrogen ions in water is this, 1 into 10 to the power minus 7, and the concentration of OH minus ions in water is 1 into 10 to the power minus 7. It's pretty small, but hey, when you add them two together, that gives you 14. 7 plus 7, that's 14. The pH scale, that's how it was actually made. Nobody gives a Praparino. Done? And last but not least, one more thing about pH. Here you go. These colors again are inverted. Please do not look into these colors as blue, वगैरह वगैरह. This is Roig Biff. This is actually opposite to what you're seeing. This is supposed to be red. This is supposed to be orangish, yellowish. This green is this neutral right here. Blue is this part here. Weakly alkaline, indigo bit, and violet bit is somewhere here. Right? It's just an estimate. See, strongly alkaline becomes around 13ish, 14ish, Weakly alkaline, roughly around 10ish, 11ish, right? So that's just that's just an estimate which is given to you by universal indicator. This 7 is neutral, gives you green. If you go towards the left, the more left you go, the more acidity you're going to have. The more right you go, the more alkalinity you're going to have, right? That's all about the pH and its idea for our use.